Hello, hello. Test, test. Can you guys hear me?
Yes.
Hello, hello. You guys hear me? Okay, perfect. All right. So let's give it one more minute, then we can get started. All right. So welcome to Alex Ivy School. Our organization focuses on providing the training services for the North American math competitions, including but not limits to like the AMC, AIME, Euclid, COMC, so on and so forth. And today we're going to focus on the 2024 AMC 12. So before we get started, we know that AMC 12 is pretty much around the corner. So our lecture is try to give you guys a very quick preparations for the upcoming exam. So our lecture is going to divide into 10 lectures. Okay. So in these 10 lectures, we're going to cover the most important concepts for the AMC 12. Generally speaking, for AMC 12, we're going to cover four major topics: geometry, algebra, counting probability, and number theory. And this is how I organize our lectures. So for each lecture, we're going to cover several different important concepts for these four major parts. Okay. And just want to give you a very quick overview of what we're going to do. For each lecture, we're going to divide our lecture into three major steps, or say three major categories. The first category, we're going to focus on the concepts. There are so many concepts for North American math competitions. There's so many things you need to remember, so many things you do not have to remember. So we'll take this opportunity to give you guys a walkthrough. We're going to pick up the most important concepts that you need to know in order to go to AMC 12. The second part is after we summarize all the concepts, we're going to give you guys a summary about the important types of questions. There are like so many questions in AMC, right? You can't really just do them one after another. You need to put them into different category. After you classify them into different categories, we're going to teach you, okay, these are so important, and what are the conditional react, like the common practice for each of this category. Give you guys like a big direction. Instead of like going the problems one after another, let's try to focus on the most important part. Okay, and the third part, we're going to give you the real sample problems. Real problems. So we need to know the fish, we need to know the strategies and the real practice. So the third part, we're going to pick up some real problems from AMC and AIME, try to give you guys, how to use our technologies, do the real problems, and then you'll be able to find out, okay, how to implement them. This is basically where we come from. And whenever we're talking about the real problems, our lecture here for this bootcamp lectures, we're going to focus on some relatively difficult problems. So generally speaking, we're going to focus on question number 21 to question number 25, especially for AMC 12, plus some mid to high complexity AIME problems. So we believe having such a combination, some relatively difficult AMC problems, plus some mid to high complexity AIME problems is really going to help you to expand your horizon and implement our technologies for some relatively challenging problems. And what about the easy ones, right? You might be asking for the questions. Generally speaking, for AMC 12, you have like 1, 2, 25, right? You have like 25 problems. For the first 10 problems, I think these are easy peasy problems. You're going to take care by yourself. From question number 11 to question number 20, these are considered to be the kind of like the medium problems. So, but still going to be easier compared with the last 5 problems. So we're going to leave this problem to our crash course. So we still have a crash course along with our bootcamp lectures. It's kind of a combination. Our bootcamp lectures focus on the difficult problems. We're going to guide you through the entire process step by step. Well, for this 11 to 20, these are considered to be relatively like the intermediate stuff. We're going to leave it to our crash course. We have a crash course. We have it every day. We're going to release the problem. You guys go there, submit your answers. We're going to give you the explanations that you can not only see my answer, but also see the other students' answer. This is more like a learning process. We're going to make it as a team. So you'll be able to use 8 weeks, 2 months, 8 weeks to go through all those mid complexity problems. Plus, our lectures focus on this high complexity problems. So this will be an overall coverage about all the problems that you need to do for the upcoming AMC12. All right. Yeah, just want to give you guys a quick overview. This is our how our lectures are organized. If everything's okay, so let's fly to our lecture number 1. So in today's lecture, we're going to focus on the first part, lecture number 1, the 2D geometries. Okay, we can use 3 lectures talking about the geometry. Today it will be 2D geometry. The next lecture will be 3D geometry, or like the solid state geometry. And the third one will be coordinate geometry. So 3 lectures talking about all the geometry related concepts. All right, if all good, let's go to our geometry part. So there are several concepts that you need to remember. So this is actually our section number 1, the basic concepts. Okay, so what you need to know in order to go to the AMC12. So the first part is fairly straightforward. You need to know the trigonometry inequality. These are one of the intrinsic properties for the trigonometry, right? So you have like any 2 sides, adding them together will be bigger than the third one. And actually, sometimes you do not have to list out all those 3 different inequalities, as long as you can figure out the minimum of 2, like the minimum 2 sides, adding them together is greater than the largest one, right? So that will be good enough. You don't have to waste your time talking about the other 2. Let's say if you know A is bigger than C, which is bigger than, like A is bigger than B, which is bigger than C, as long as you can have A plus B, B plus C greater than A, then you're good. You don't really have to waste your time about the other 2 inequalities, right? This is good enough. So trigonometry's inequality is actually one of the intrinsic inequality for any given triangle. So this is actually one thing you need to remember. And on top of that, there's another very important intrinsic inequality for any given triangles is the trigonometry. Let's say I have a triangle, I got a theta here, then sine theta must be from 1 to 0. Cosine theta must be from 1, 0. Right? These are actually the most important intrinsic inequality. So why I'm introducing this? Because you know what, from time to time, if you just given like a random triangle without any specific features, and you really have to build up some inequality to squeeze out some specific range. So using this triangle inequality and this trigonometry inequality really going to help you to getting started. You need to build up the inequality and taking from there, solve the problem. And this is actually the vector form for our triangle inequality as well, right? If you consider these 2 sizes, x and y, and 2 vectors, you'll be able to have such a relationship. All right, this is the first part. Well, the second part will be the Pythagorean theorem. Pythagorean theorem is something you learn from your elementary school, right? We don't have to talk too much. Like right triangle, you have such a perfect square relationship. Well, most of the time in AMC, they won't really give you a direct right triangle and then ask you to determine, okay, I have A, I have B, what is the value for C? In the real practice, it's going to be the other way around. Most likely, the question is going to give you a triangle with 3 sizes. Maybe the question give you directly, or maybe you need to do the calculation during your derivation process. But no matter what, you're going to figure out a triangle with 3 sizes A, B, C. And then you need to figure out if those 3 sizes can create a Pythagorean triple, then this triangle becomes a right triangle. So it has to be 2-way around. Give you a triangle, do the Pythagorean calculation, or more importantly, I give you 3 sizes, then you must be able to determine, okay, this is actually a right triangle. And then taking from there, you might use this 90-degree to do a lot of flowery calculations thereafter. Okay, I have already listed out there are so many Pythagorean triples, but you don't really have to remember them all. There are several things I like to list them out. These are the Pythagorean triples that were tested in AMC in the last 20 years. So try to remember, at least get yourself familiar about these 5 Pythagorean triples. Okay, as long as you see them, you can realize, okay, this is going to be a right triangle. Okay, moving forward, the third part, angle bisector theorem. This is extremely important these years. Trust me, as long as you see the question give you angle bisector, 99%, especially in these days, 99% you can use the angle bisector theorem. So what is the angle bisector theorem? Let's say you have an angle bisector AD, right? And then you're going to have what? BD over DC equals to AB over AC. Trust me, this is extremely important. As long as the question gives you angle bisector, 99% you're going to use the angle bisector theorem. Remember that, okay? And also on top of that, these days, angle bisector plus the Menelaus, these are becoming more and more important. Okay, we're going to talk about the Menelaus in a bit. But generally speaking, from question AIME, question number 5, question number 7, you're going to keep seeing problems from Menelaus to angle bisectors or combination between the two. This is very important. And AIME, question number 5 to question number 7, just roughly AMC12, question number 20, number 21-ish. So the complicities are totally within the AMC12. Okay, maybe something 21, 25, like for question 21, 22, 23. Yeah, pretty much around this AIME 25 to 27, like AIME number 5 to AIME number 7. So try to remember Menelaus and angle bisector are actually something so important. Okay? Yeah, because I assume, guys, that you guys want to go to the AMC12, you already have some basic understanding for all those concepts. So we're not going to give you guys the detailed, ABC explanations. So we just want to do some high-level summary. That's good enough. All right, the other one is like the stillward. Stillward is actually a very important and also very intrinsic property for any triangles. So what is like stillward? Stillward means you have a triangle ABC, and then you have a random point D on the, let's say, on the bottom. Then you have, this is A, B, C, D, M, N, right? Now you have like 1, 2, 3, 4, 5, 6 segments, right? Of course, M plus N equals to A. There's a certain relationship. But generally speaking, you have 6 different segments. So these 6 different segments, they build up a relationship. The relationship is M times A times N plus D times A times D equals to B times M times B plus C times N times C. So this is like a relationship between those 6 segments. So how to remember, right? This is not really easy. So how to remember? There's a very short way. You can remember a man and his dad put a bomb in the sink. So this is the way how you remember such a stillward theorem. So that being said, stillward theorem is actually a very intrinsic theorem for the entire triangles. It does not really ask the triangle has to be isosceles or right. No, whatever triangles. And because those 6 segments, they have such a relationship. So that being said, as long as you have 5, you will be able to determine the last one. Is it right? You can just basically plug in into such a stillward relationship, then you will be able to determine the last one. So this is actually a very important thing. It's really going to help you to do some complicated problems from time to time. Okay, and instead of like remembering the stillward, there are also 3 specific conditions I want you to remember. So what I mean specific conditions, because stillward is actually very generic. It has nothing to do with any specific shape of the triangle or addition conditions, so on and so forth. But what if I want to give you I want to make the condition a little bit stronger, like strengthen the condition like a little bit. What about AD is an angle bisector? Okay, so for now, D is not a random point on the bottom BC, but AD is an angle bisector. So therefore, you should have a famous angle bisector length theorem. Means you can use this theorem to determine the length of the angle bisector. So AD squared will be equals to AB AC minus BD DC. Look, this one is much easier compared with the original form of the steelwork, right? Because steelwork is actually a very generic form. But the angle bisector, you already know that AD is an angle bisector, so calculating AD will make it a bit more faster. The other one, what if like AD is actually a median, right? For now, AD is no longer an angle bisector, it's like a median. So you have the famous, the median length theorem. That is 4AD square equals to 2AB square plus 2AC square minus BC square. Okay, this is how to determine the length of the median. And then what about AB and AC? They are the same, isosceles. Okay, you have an isosceles triangle. At this moment, AD can still be a random guy, it doesn't matter. But AB and BC, you're actually looking at an isosceles triangle. So now AD's form can also be further simplified into this. Okay, so these are three very important theorems I want you guys to remember. In our regular lecture, because we have a bootcamp lecture, we have a regular lecture. In our regular lecture, we want to give you guys a detailed explanation, the proving process, step by step. But here, we don't really have that much time. I just want to give you this conclusion right away. Try to remember this. This is really going to help you to expedite your calculation from time to time. All right, so this is number 4, steelwork. And then number 5, we like to talk something about the centroid, because we know we have different centers for triangle. We can have the incenter, circumcenter, orthocenter, centroid, right? Trust me, centroid is the most important, the most interesting center. It has more flowery properties compared with the others. Okay, so for the centroid, basically, these are like the intersection about 3 medians, right? Intersection about the 3 medians, as you can see from this graph. Okay, so one of the most important property, and which has been tested so many times in AMC, is that G actually divide all the 3 medians into 2-to-1 ratio. Is that right? So let's say, use different color. This is 2-to-1. This is 2-to-1. And this is 2-to-1. Why I'm using different colors? Because whenever I say 2, the blue 2 and the green 2 and the black 2, they're not the same, right? Because you have like 3 different mediums. But within this one median, the blue 2 and 1, this is basically a 2-to-1 relationship, right? The same thing applies for 3 different mediums. The centroid actually cut all the 3 medians into a 2-to-1 ratio. This is actually something very important, and AMC tested from time to time. And one more thing is that if I give you the coordinate about all my 3 vertices, okay, then how to determine the coordinate of my median? This is actually something so easy. You just use the average of the 3 x coordinate, the average of the 3 y coordinate, you'll be able to do it right away. Okay? So also another thing is the median is what we call a mass center. Means all the gravity of the shape actually centralized for the median, right? You can actually use your finger to poke on the median, and then this triangle will be balanced itself from there. So these basic properties were heavily tested in the AMC. For instance, if you go to 2018, AMC 12B, question number 13, it just basically used these properties. As long as you use this, you'll be able to solve the problem in maybe 10 seconds. All right. So this is number 5. We want to talk about the centroid of a triangle. And then number 6, we're going to talk something about the congruency. Congruency, similarity, these are the twin brothers, right? They're so important for all those kind of like trigonometry or like geometry, any kind of concepts. So basically, there are certain determination rules to determine 2 triangles that are congruent to each other. I think for our level, you definitely know that inside out. 3 sizes: side, angle, side, angle, side, angle, 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 side. So for RH side, this is especially for right triangle, right? As long as you have 2 right triangles, you just take 1 leg and 1 hypotenuse. As long as they are equal correspondingly, you'll be able to declare these two right triangles are congruent to each other, right? And also you should know that, right? SSA is not a sufficient way to determine two triangles that are congruent to each other, right? Because as you can see here, I can create two triangles. They both have one side 11, one side 6, and one of the opposite angle reaches 30 degrees, right? So you can end up creating two different triangles. They both fit SSA. So SSA is not a correct way to determine two triangles that are congruent to each other. I assume your teachers from day school has already explained this inside and out, right? So we don't have to spend too much. So generally speaking, you'll be able to find out in order to determine two triangles that are congruent to each other, at least you need a side information, right? You can't only have angles, you need to have at least one side to determine two triangles that are congruent to each other, right? These are something you know from your elementary school, so easy. All right, after congruency, we're gonna go to our similarity. Similarity is actually one step forward compared with the congruency is actually more generous. If I want to determine two triangles that are similar to each other, you can just have two angles or two sizes with their included angle and also three sizes. Okay? So these are actually something, I think these are something more applicable for, right? All those like triangles, stuff like that. So if you want to do comparison between the congruency and the similarity, you're going to find out that congruency has more rules, right? But similarity does not have that number of rules because something like AAS, ASA, these are, as long as you have two A's, right? You don't really have to worry about too much. Two A's is good enough to determine two triangles that are similar to each other. So there's no need for you to do an extra calculation, extra like condition to have a side information, right? So in our regular lecture, we actually give you guys 12 different patterns how to determine two triangles that are similar to each other. We have this you have this like pyramid shape, you have like this angle shape, all those kind of things. But for now, we don't really have time to go for this 12 different patterns. But generally speaking, you need to know that as long as you have two triangles, you need to know how to determine those two triangles are similar to each other, right? So these are so many like that, like the birdie shape, like this, all the kind of things. This is all over the places. So as long as you know, I think your day school should already give you the summary as well, how to determine two triangles that are similar to each other. Yeah. Well, I'm actually in my lecture. If you have any questions, you can let me know. You can actually type it or you can just unmute yourself, ask a question. I see somebody got a question. There's the same problem for sine. Okay. I'm going to check it out. Yes, that's pretty much. Yes, we have like a lot of similar problem for trigonometry and the geometry. They originate from the same concepts. All right. So these are the similarities, congruencies. Okay, moving forward, another very important rule, actually two important rules, right? You just kind of see them from time to time in parallel. One is Menelaus, one is Siva, right? So for Menelaus is actually, I have a triangle, let's say ABC, and this triangle was cut by a transversal line, right? A transversal line. And this transversal line cut my triangle at two sizes, R and P, and also intersect with one of the extension side, right? The side extension outside the triangle. As long as you have this, you'll be able to have such a relationship. Here over here, here over here, here over here, right? Putting them together is going to be equal to 1. This is actually something very important, especially, like I said, AIME, the first couple of AIME problems really like to test you the Menelaus. Also, Menelaus is an intrinsic property of a triangle. It has nothing to do with any shape, any type of the triangles. Student got through. Are we going to see some questions, examples today and go? Definitely. Question is our number one important thing. But before we jump to the question, I know some lectures, they just go for questions one after another, but we like to do some summary concepts before we jump to the question. Definitely, we're going to go for the questions. That's where we come from. Okay, so moving forward, the Siva. The Siva theorem is also very important. You got a triangle and you got a random point in the middle, right? As long as you have this, you basically make 3 connections, extensions, then you have what? BD over DC and CE over AE, AF over FB. They will be putting them together equal to 1. This is exactly the same thing as the media loss. So media loss and CVAR, they're quite similar for those 2 rules. And then, like I said, they're all like tested maybe in AIME question number 5 to number 7. This is pretty much in the same range, the same complexity range of our AMC12. All right. So moving forward, 2 very important rules, the sine law and the cosine law. These are so important, they're going to really test you from time to time. Okay. For the sine law, you know, A over sine A, B over sine B, C over sine C equals to R. This R is actually the radius of the circumcircle, right? The radius of the circumcircle. And the cosine law, I'll take one as an example. Let's say cosine A equals to B squared plus C squared minus A squared to BC. This is actually a very important rule because it builds up the relationship from side to angle. You see, on the left-hand side is only angle. On the right-hand side is only side. So the cosine law is actually a liaison which builds up the relationship between the pure side relationship to pure angle relationship. This is actually something very important. Sine law, cosine law, and even Pythagorean theorem, these are so easy, but trust me, they will be tested every single year. So important. All right. So this is number 10. Let's go to number 11. From number 11, we're going to go to the circle part. Okay, so the first part we're going to talk about is the power of a point. Okay, so power of a point is actually a series of theorems, right? It has actually 3 theorems. The first one is the chord theorem. So as long as you have 2 chords intersecting with each other, you're going to have DE, EB equals to AE, EC, right? This is quite easy. The second one is the tangent secant theorem. You have a tangent, you have a secant from a point outside the circle, right? Then you have what? AB squared equals to BC times BD. Okay? And then moving forward, the third one is actually our secant rule. So from one point outside the circle, you want to make 2 secants. You have like CB, CA, CD, CE, right? As you can see, these 2 guys are actually very similar because as long as you make one secant closer, 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 all the way, whenever it degenerates into a tangent, so your secant rule degenerated into a tangent rule, right? And these are something so easy, so I don't want to spend too much time with you guys. You guys already know that. Okay, there's only one important thing I want to mention is that let's try to do a summary. Whenever you see a tangent in the math competition, what are you going to do? What is your conditional react as long as you see tangent in the AMC12 math competition? So whenever we talk about the tangent, there are 2 scenarios. One is you have a line tangent to a circle. Or you have maybe 2 circles. They can be externally tangent to each other. They can be internally tangent to each other, externally tangent to each other. Or you have another shape. It's like this. I'm going to show you. Okay, so they are externally tangent, but there's a common tangent line between 2 of them. All right, so as long as you see 3 different shapes, I'm going to show you the conditional react that you need to do one after another. The first one is fairly easy. You always want to do a connection between the circle center to the tangent foot. Yeah, I see many students already have the correct answer. This is extremely important because as long as you do the connection, you have a right triangle, you have a right angle right away, right? What about you have 2 circles? They're internally tangent to each other. You're going to do 2 things. First, connect with the 2 circle centers, and then you can do an extension to make it still all the way to the tangent foot. Because as long as you do this, you'll be able to find A and B L, A and B is perpendicular to L, right? Same thing. Do a connection between two circle centers, make an extension all the way to the tangent foot. So this line, this connection between two circle centers will be perpendicular to the common tangent line. What about two circles that are externally tangent to each other? Pretty much the same thing. You want to do a connection, right? Same thing. This connection will make up a segment AB, and this AB is going to be perpendicular to L as well. Okay, then what about this? You have two circles externally tangent to each other, and they have a common tangent line. You know what? We just follow the same thing. As long as we have a circle tangent to a line, we just make a perpendicular line from the circle center to the tangent foot. Okay? As long as you see two circles that are tangent to each other, try to connect these two circle centers. Now, I'm going to do a little thing. From here, I'm going to make a perpendicular line from the smaller circle center to the bigger circles radius. Okay, I want to make a quick perpendicular line. As long as I do that, this is going to be a rectangle, right? This is going to be a rectangle. And this is going to be what? A right triangle. Okay, let's do some quick number crunching. So let's say this guy has a big R, this guy has a small r, talking about the radius. So this is going to be what? Big R plus a small r, right? This is the circle center connection. And this is going to be big R minus a small r, right? Because because this is R, small r, this is going to be a small r. The blue part is a rectangle. So that being said, you're actually looking at a specific red right triangle, a red right triangle. The red right triangle, I'm going to drag it out. This guy is big R, small r. This guy, big R minus small r. So that being said, the other leg will be 2 under root big R small r, right? 2, I'm going to use the color maybe blue. 2 under root big R small r. And here, same thing, 2 under root big R small r. So that being said means what? Okay, if you have two circles, they're externally tangent to each other, you have a common tangent line, the length of your common tangent line is solely determined by the radius of these two circles. Is that right? So the length is 2 times root big R small r. Okay, and you know what? This little red triangle we give a name. This is a magic triangle because a lot of AMC problems can be easily solved using this magic triangle. We can have a look at it whenever we're getting there. Okay, so always focus on this little magic triangles. You'll be able to expedite your calculation process significantly. All right, so let's continue to number 12, cyclic quadrilateral. You know, any triangle, you can basically find out a circumcircle, right? Regardless, whatever triangle it is. You can always find a circle to make sure the 3 triangles, like 3 vertices actually falls on the circle. But it's not the case for quadrilateral. Not all the quadrilaterals can be inserted into a circle. Make sure these 4 vertices falls on the same circle, right? So there are certain types of quadrilaterals. They can be put it into a circle. Make sure the 4 vertices are all in the same circle. So these quadrilateral, we give a name, cyclic quadrilateral. There are so many ways to determine a given quadrilateral is a cyclic quadrilateral. And the cyclic quadrilateral also have so many interesting properties. We have already given a lot of detailed explanations in our regular lectures. So here, I just want to give you some high-level things, the most important things. As long as the opposite 2 angles, they are supplementary, right? Adding them together equals to 180 degrees, then you can claim this is a quadrilateral. This is like cyclic quadrilateral. And the same thing, if you have a cyclic quadrilateral, the opposite 2 angles of this quadrilateral, adding them together will be equals to 180 degrees. So this is a sufficient and necessary condition. The other thing is, let's say I have these 2 angles, they're facing this guy, and this guy, they're all facing to the same side, DC, right? As long as these two angles facing to the same size, they are the same in measurement. So you can claim this is actually a cyclic quadrilateral. The same thing applies. If you have a cyclic quadrilateral, like whatever two angles, as long as you're facing to the same side, you must be the same in measurement. So again, this is also a necessary and sufficient condition. Okay, there are so many other determination rules, so we don't have to cover them all, but these are the most important things from an angles perspective. And also, if the question gives you a cyclic quadrilateral, and ask you to determine the area, so you can actually do a shortcut. So let's say if this is A, B, C, D, four sizes, so the area of the cyclic quadrilateral will be under root S minus A, minus B, minus C, minus D, where S is the A, B, C, D, putting them together, divided by 2. This is something quite similar to Heron's formula, right? Heron's formula. Heron's formula said if I give a triangle ABC, right, then you'll be able to basically find a P minus A, P minus B, P minus C, right? P is actually half of A plus B plus C. So this is like the Heron's formula, right? So that being said, Heron's formula is for triangle, and my formula now is for the cyclic quadrilateral. They both basically follow a similar pattern, okay? A student got a question. For the second condition, do all four angle relationship needs to be satisfied or just one? No, one will be good. For the second one will be good. They'll be good enough for you to determine this is actually a cyclic quadrilateral. You don't have to make all of them fit. Because as long as one is fit, all the others will be fit automatically. Okay? From a determination rules perspective, one pair will be good. Okay, so this is the cyclic. And the other one, of course, as long as you're talking about a cyclic, Ptolemy rule is very important, right? Ptolemy theory says if you have a cyclic quadrilateral, what are you going to do? The product of two diagonals must be the same as the sum of the product of the two opposite sides. AB times CD plus AD times CB. Okay? So any cyclic quadrilateral, the diagonals, product them together is the same as the product of the opposite two sizes. Also, this is necessary and sufficient. If I can get a triangle has such a property, it will automatically say this is a cyclic quadrilateral. Okay? And then number 14, we're going to talk something about an important topic, which is the area. Because as you can recall, if you go to AMC, most of the geometry problem will be focused on the area. They're going to really ask you to determine the area for different shapes, not necessarily triangle, but sometimes some quadrilateral or some polygons. So having a good understanding how to determine all the areas are very important. Okay, there are several ways I like to list them out. The first way is actually using the definition. This is like so easy, nothing to say. And the second part is just like I said, using the Heron's formula. Heron's formula is you have three sizes, right? And you do not really have to determine the height. You can just basically calculate the area directly from the three sizes. And another one is actually the famous shoelace. This is more like from the coordinate geometry, right? As long as I give you the coordinate of the three vertices of a triangle and ask you to determine the area of this triangle, there's no need for you to basically using the distance rule, figure out the length, and then do a Heron's formula. That's going to take forever. You can directly using the shoelace, right? Simply using the coordinates of the three vertices, you'll be able to figure out what is the area of this given triangle. And this is actually only for the triangle. You can make it more generic. Any kind of convex polygon in the 2D in the Cartesian plane, as long as you know all the vertices coordinate, you'll be able to use a generic way to determine the area of such a polygon. Okay, it has to be convex. Okay, as long as it's and like convex polygon with all those vertices, you'll be able to use this more generic way to determine the area. Okay, this is something you need to remember. This is good. And what else? This is also important one, right? As long as you have a trigonometry here, so let's say you have two sizes, A and B, and you know the sinusoidal value of this included angle, so the area could be calculated like this, right? You don't really have to do the calculation from the very beginning. You can just directly do AB sine C. That's exactly the area of this triangle. And also, as long as you see two triangles, one with a yin circle, one with a circumcircle, you can also expedite your calculation to determine the area without jumping to the height to the bottom. If you know the size, like the what is called, if you know like the radius of the yin circle, okay, like the radius of the yin circle, and then you know S is part of A plus B plus C, then using R times S, you'll be able to determine the area of the triangle, right? You know the yin circle's radius and also the three sizes, adding them together, you'll be able to determine the area of this triangle. And the same thing, if you know the three sizes, A, B, C, and you know the length of the, like the radius of the circumcircle, you can also use another formula to determine the area of this triangle, right? Three sizes plus the radius of the circumcircle also going to help you to determine the area of a given triangle. So these are actually something very important I want you guys to remember. They're going to test you this from time to time. Okay, so far so good. All right, and one more thing before we moving forward, I think from a geometry's perspective, from time to time, I really want you guys to remember some trigonometry related values. Of course, you guys all know this 30, 45, 60, 90, right? But these are not good enough. If you can know more trigonometry values, sometimes it's going to help you save your time significantly. So today we're going to give an example. This is like a 2020, this is 2023, our latest and greatest AMC 12B, question number 25. If you know a specific triangle's trigonometry value, you can solve the problem maybe in 30 seconds. But if not, you want to go the traditional, typical trigonometry way, you can maybe spend up to 20 minutes to finish that problem. So what are the important trigonometry values that you need to remember on top of the ones that we already talked about? These are the angles. Very important. I want you guys to remember them all, especially for your level. 15 degrees, 18 degrees, 36 degrees, 54 degrees, 72 degrees, and 75 degrees. I'm talking about the sine value, the cosine value, and the tangent value. So let me help you to reduce because there are like so many values, right? Now, let me help you to reduce the complexity because there are some things you can just basically ignore them. First, for sine and cosine, as long as you know the sine and cosine, for all the tangent values, you can do a quick division, right? You don't really have to remember that specific tangent value. You can do it by yourself. Second, you see, using the core function, the sine 15 degrees will be the same as the cosine 75 degrees. Cosine 15 degrees will be sine 75 degrees. So that being said, as long as you know 15, there's no need to remember the 75. Is that right? The core function already helped you to simplify the process. Then what about 18 degrees? 18 degrees is the same thing as 72 degrees, right? As long as you know 18, you know the 72. So no need to remember 72. I'm going to use the other color. And then the same thing, 36 and 54, right? As long as you know 36, you don't have to remember 54. And even for those three remaining, 15, 18, and 36, you can use the double angle formula, right? As long as you remember anything for 18 degrees, you use the double angle formula, you get automatically for the 36 degrees. Is that right? So again, no need to remember the 36 degrees. Okay, voila. You see, now we have already confined, right? We have like so many things at the very beginning, but at the end, I just want you to remember these four numbers. Sine 15, cosine 15, sine 18, cosine 18. All the other stuff, you can do a quick calculation, figure out by yourself. So far, so good? So later, I'm going to give you some examples, and you will realize if you remember this, it's really going to help you to expedite your calculation significantly. Okay, so that being said, we use like 40 minutes or something, wrap up all the important concepts that you need to know. If you already know this, perfect. But if you forget one or two or something, it's a good opportunity. I'll help you guys to kind of like a recap. These are the important stuffs. So this actually finished our part one. So let's go to our part two, the important types of questions. So whenever we go to AMC12, talking about the 2D geometry part, there are three major stuffs that you need to remember. They basically test you for the three major categories. The first one is actually the use of some important theorems. You know what? Actually, I find out Pythagorean theorem, sine law, cosine law. These are the three most important theorems. As long as the question gives you this, you'll be able to use it. Plus angle bisector. Angle bisector is not something important or not important. It's a must. As long as you see angle bisector, you're going to use the angle bisector theorem. Okay? The first three are important. The last one is kind of like definitely. As long as you see the condition, you're going to be able to use it. The second part is, as long as you see similar triangles, most of the time you can use the similar triangles area ratio is the similarity ratios for fixed square. Okay, two triangles that are similar to each other, and the question asks you to determine some area-related stuff. Similarity ratios per fixed square is going to be the area ratio. Of course, the volume ratio will be the similarity ratios per fixed cube, right? The question tests you volume, not that much, but yeah, they test you like once or twice historically, but generally speaking, is like the area ratio. They test you more about that. Okay, this is the second one. As long as you see similar triangles with some area stuff, most likely you're going to use such a condition. And then the last one will be more some circle, some tangent, some Ptolemy, all those kind of combinations. You're going to see that from time to time. So you need to remember all those conditional react. As long as you see two circles that are tangent to each other, how you're going to do the connections between the circle center, from the circle center to the tangent foot, so on and so forth. That's really going to help you to expedite your calculation significantly. So these are generally speaking, the three major problems we're looking at from time to time in the AMC12. So the next step is we're going to give you some sample problems for each of this category and then guide you through the thinking process, how to deal with all those problems. All right? So let's go to our section number 3, real problems. Okay, we always from the concept, go to the classification, then go to the real problems. So first thing first, some important theorems. Like I said, what? Pythagorean, sine law, cosine law, angle bisector, so on and so forth. So let's have a look at it, our first problem. Okay, our first problem is a problem that comes from 2022 AMC12B, question number 25. Trust me, even though this is like a question number 25, but this is a super straightforward problem, as long as you know all the strategies that we introduced. So the problem says there are four regular, okay, I'm going to highlight the questions whenever I'm reading it. There are four regular hexagons surrounded by a circle, surrounded by a square with a side length 1, okay? And each one sharing an edge with the square as shown in the figure below. The area of the resulting 12-side outer non-convex polygon can be written as m under root n plus p, where m and p are integers and it's not divisible by the square of prime. So what is the value for m plus n plus p? So long story short, they need to ask you to determine the area of the entire outer shape, right? The outer shape is like a 12-size thing. Well, as long as you see such a problem, so don't be panicked, right? Because this problem is just like surrounded by the hexagon, a bunch of hexagon, putting them together, do some stuff. And a very first side of this problem, you can find out the ultimate shape, the 12-sided thing, is actually a very symmetric thing, right? It's a very symmetric thing. So therefore, I get a hint. Instead of like calculating the entire thing as a whole, maybe let's try to just cut it because it's like so symmetric. Maybe I just try to cut it into a small piece. As long as I figure out the size for a small piece, I just basically multiply, like, right, double size, like 8 times, 6 times, like whatever, then I will be able to get what I need. Right? I think this is a very intuitive thinking process. You don't really have to go for the entire thing. Just try to make it as easy as possible. So how to make it symmetric? How to cut this symmetric shape? I think very intuitively, you can actually do from here. This is one time you can do a cut, right? The top one and bottom one, they're the same thing. And also, you can do the second line like this. Okay? Can I do a bit more? I think so. Now we have like 4 shapes, right? But I can just do another cut from here. I think, right? I actually cut my entire shape into 8 little shapes. So what is my little shape? Let's focus on this. Maybe I'll use the color green. Maybe yellow. This is basically my shape, right? As long as I figure out the size for this yellow shape, I times 8, I got what I need. That's it. Well, for this yellow shape, this is like a quadrilateral, right? But it's not a very regular thing, right? I like to deal with triangles. I like to deal with maybe some easy quadrilaterals. This is something not so easy, so regular. It's not so easy for me to finish my calculation. So that being said, this is a very important thing is you always want to cut the irregular into regular. Okay? As long as you see some irregular shapes, always cut into some regular shapes that you can easily deal with. Is it easy for me to cut it into something that I can easily deal with? I think so. This is not rocket science. I'm going to use the color here. Let me try to do a very quick connection from here to here. Now I actually cut this yellow shape into 2 parts. One is the blue shape here. One is the red shape here. Is that right? My blue shape is actually a trapezoid, right? And my red shape is actually a triangle. Of course, these guys are much easier compared with the original yellow ones. So I'm going to say that I'm going to cut into a blue trapezoid and a red triangle. Is that right? Okay. So now my goal is try to determine what is the area for this trapezoid and what is the area for this triangle. That's it. So in order to do that, I have to give some denotation. This is B. This is B. This is A. This is C. This is O. Okay, let's jump to the trapezoid first. D, B, C, O. To determine the trapezoid area, you need the top, you need the bottom, you need the height. Okay, so let's do this one by one. Then what about the first? What about the height? I think the height is easy, right? The height is here. The height is actually half of my side, right? My side is the same thing. The question already said this is actually 1, right? So this is 1/2. This is 1/2, right? So therefore, my BD equals to 1/2. This is easy peasy, right? Okay, then how can I determine like the BC and DO? How can I determine BC and DO? This is not a rocket science as well. Let's have a very quick look at it. Where does DO locates? DO is actually part of this line, right? Part of this line. This is what? This is actually the height of one of my hexagon, right? This is the height of one of my hexagon. This is so easy. If I give a hexagon, how can I determine the height? This is something so easy, right? I'm gonna write it here. This is my hexagon here, here. So if I give you the size is A, who can tell me what is the height of this hexagon? This should be 120 degrees, right? So what is, yeah, I see Gabriel has the answer. √3, right? So easy. Yeah, because I know that my hexagon has 1 as the side length, so the height will be 1. If the height is 1, what about this part? This part is actually 1/2, right? It's part of this small circle thing. Circle. Don't forget this is like a circle. So therefore, the value of OD is actually what? √3 minus 1/2. Right? √3 minus 1/2. I'm going to write it here. This is √3 minus 1/2. This is 1/2 as my height. And then who can tell me what's the value for BC? What's the value for BC? √3 minus 1, right? Because BC, you have to subtract this part. This is 1, right? So have √3 minus 1. I'm going to use the thinner. √3 minus 1. Okay, now for your trapezoid, DBOC, you already know the top, you already know the bottom. Then it's time for you just to determine the area. This is something so easy, right? I'll let you do the calculation. The first part you're done. The blue part you're already done. So now it's time to deal with the red part. The red part is actually a triangle, right? A red triangle. For the red triangle, let's have a look at it. We're going to deal with that. Okay, I'm going to put it here. My red triangle, I already know that BC is actually equals to √3 minus 1. My blue part, right? My black part, √3 minus 1. If I want to determine the area of this triangle, I really need either some side information or some angle information, right? I can't really figure, I don't think I can just figure out like the bottom, the height or something. Okay, I already know one side, which is BC. So who can tell me, is it easy for me to get maybe other side information like AB, AC, or some angle information? Either way, right? As long as I got either way, I can determine the area. That's it. Who can tell me? Is it easier for me to get the extra side information like AB, AC, or the angle information will be good? Yeah, I see Gabriel has the correct answer right away. It's going to be Side. It's going to be the angle information is easier because look, we have the regular hexagon, we have like the square. There's so many nice, very nice angles there waiting for us, right? So we should use that. So what kind of information can I get? This part. I'm going to use the color maybe blue. This part is 45 degrees, right? Because this is the vertex. This is the vertex angle for x, right? This is 45 degrees. And this is what? What is the angle for this? This is easy, huh? This is what? This is a regular hexagon, right? Regular hexagon. What's the angle for this little blue one? 30 degrees, right? 30 degrees. So this is 30 degrees. Oh, now I have it easy. Look, I'm just going to drag it out. My BAC, I know the side is √3 minus 1. I know this is 45. This is 30. This is what? 105, right? So you would be able to determine all the sizes using what? The sine law, right? Sine 105 over √3 minus 1 equals to sine 45 equals over AB sine 30 over AC. Is that right? Okay. I'm okay for 45. I'm okay for 30. Then what about sine 105? Sine 105 using your core function equals to what? Cosine 15 degree. Is it right? Cosine 15 degree. This is exactly what I mentioned. You need to remember some easy things, right? √6 plus √2 over 4. Okay? As long as you know this, you can easily figure out all the three sizes of your triangle. Here. Look, this is like a high-level lecture. We don't want to go for the super details. I just want to give you some high-level thing. You do all the calculations yourself, okay? We just want to go the thinking process. So now you know, okay, a triangle, you already have three sizes. You already know the angles. You use whatever you like. AB sine C, or use Pythagorean, or use like whatever. You can figure out what's the value, right? So now you can easily figure out the value for this little red triangle. Look, you have a blue, you have a red, adding them together, you have the one prototype of the shape. You use the value times 8, you get what you need. Does it make sense? So far, so good? So that's it. That's the solution for such a problem. Look, this is question number 25, but there's nothing flowery, right? You're not using any complicated thing here and there, just some basic formulas. You need to remember the like sine law, cosine law. You need to remember some specific triangles trigonometry value, then you're good to go. Okay, some basic. So not all the last problems are very flowery, complicated stuff. Sometimes you can use some easy peasy process. If you check the AOPS, they have different solutions. Sometimes can be very complicated, but this one I think is very easy, very understandable. Okay, this is our first sample problems. Yeah, let me know whenever you have any questions. Okay, so you can chat with me. You can just unmute yourself. I really like you guys to all participate in the discussion process. So if all good, let's go to a second problem. Second problem goes like this. Yeah, this is a problem that comes from 2013 AMC12B, question number 24. Okay, so let's have a look at it, how this problem is talking about. So this problem says, let ABC is a triangle with M is the midpoint of AC. Okay, I'm going to highlight it. M is the mid of AC. And the CN is the angle bisector. Okay, like I said, as long as you see angle bisector, you're definitely going to use the angle bisector theorem. I'm going to put it here. And let X be the intersection of the median BM and bisector CN. In addition, BXN is an equilateral triangle with AC equals to 2. So what's the value for BX squared? Okay, let's try to have a look at it, how this question is like how this graph looks like, right? All those trigonometry problems, you need to have a nice graph. I have something like this. Oops. Something like this. Okay, I have a triangle here, here, here. BM, this is the median. This is the angle bisector. Okay. You have a triangle. This is B, A, M, C, N, X. Okay. M is the median. I'm going to put it here. And the CN is the angle bisector. They intersect at X point. And this BXN. BXN is a 90 is what? Equilateral triangle, right? Okay, my graph is not super perfect, but you got an idea, okay? Equilateral means all the sizes are the same, and these are 60 degrees, 60 degrees, 60 degrees. With all of information, the question asks you how to determine the value for bx. I'm just gonna put bx here. Okay, so let's have a quick look at it. What are you gonna do, right? So first, I mentioned that as long as you see angle bisector, you're probably going to use the angle bisector theorem. I'm going to put it here. This is our conditional react. Angle bisector theorem. Okay, angle bisector theorem. So CX is the angle bisector for two triangles. One is the BMC, the other one is the ABC, right? So therefore, you know what? My suggestion is you just write out all those possible angle bisector relationships for all the triangles. You might use them all or might not. It doesn't matter. You just write them out. So for triangle BMC, you have BC over MC equals to BX over XM. I'm just gonna write it here, okay? In triangle ABC, you have BC over AC equals to BN over NA. I'm just gonna write it out, okay? Next, I used the angle bisector already. The next condition is what? M is the mean. M is the mean. AC is equal to 1, so this is 1. This is 1, okay? I'm just gonna write it here. Nothing really special. What else? I use the angle bisector. I use the M as the mean. The question asked me to determine BX. Well, let's do a very quick analysis. Let's have a quick look at it. The question also has another condition. The red triangle is a equilateral triangle. Equilateral triangle, I know the three sizes are the same. That's definitely no problem. And it also has some angle information, right? How can I put them together, try to tweak, make it work? Let's have some quick look at it. Let's have a quick look at it. Because this is an angle bisector, so you have angle 1 equals to angle 2, right? These are definitely the same thing. But did you find out for such a problem, these two triangles, these two angles, are there anything special for these two angles? Did you find these two angles are a little bit special? Because for this angle, it equals to what? 60 degrees minus angle 1. Is that right? 60 degrees, the exterior angle equals to the sum of two non-adjacent interior angle. And this angle is the same thing, right? It also equals to 60 degree minus angle 2. But angle 1 and angle 2 are the same. So that being said, for my angle, maybe I'll give you name angle 3, angle 4, you can find out angle 3 is actually equals to angle 4. They both equals to 60 degrees minus angle 1, 2. Okay. If that's the shape, it actually goes to one of our, I think previously I mentioned, for the similarity, we have summarized 12 different patterns. And this is one of the birdie pattern. As long as you have angle goes like this, these two angles are the same. And they are sharing the same top angle. So these trigonometries are similar to each other, right? These two these two triangles are similar to each other, right? And this is exactly the same thing. You can find out, obviously, triangle BMC is similar to triangle ABC. BMC is here. ABC is the big one. Okay, I'm going to remove that. As long as they're similar to each other, you have the proportional relationship, which is what? BC over MC equals to AC over BC. So therefore, BC equals to MC times AC. BC squared equals to MC times AC. MC is 1. AC is 2. All right, BC equals what? BC equals to root 2. BC equals to root 2. Okay, good. You have some extra condition get. Okay, BC equals to root 2. Okay, so now I think we just use our similarity to contribute another value for BC, but our ultimate goal is try to figure out a value for BX, right? I don't need BC, I need BX. So let's have a quick look at it. The angle bisector already give us two relationships. Let's have a quick look at it, how this relationship can help us maybe simplify or easy the problem. BC over MC equals to BX over XM. BC is what? BC is root 2, right? MC is 1. BX over XM equals to root 2 over 1. Okay, what else? BC over AC equals to BN over NA. BC is actually root 2. AC is 2. BN is here, okay. NA is there. Okay, so let's try to do a quick analysis. Let's say my goal is try to determine the value for BX, right? So for the remaining segments, I want to be maybe just using BX or something, try to representative. Right? I don't want to have like too many variables all over the places. Let's try to streamline all the variables, right? Because using this yellow one, you find BX over XM is root 2 over 1. So you can let maybe XM equals to A, then BX will be root 2A, right? Root 2A. This makes sense. And then BN over NA is root 2 over 2. BN is the same as BX, right? Because they are all coming from the equilateral triangle. So BN is also root 2A. And NA will be root 2 times root 2A. So this is going to be your 2A. Does it make sense? So this is root 2A, this is 1. Right? This is not a rocket science. You'll be able to find it right away. You just use some simple relationship between different segments, you get what you need. But wait, what is your goal? Your goal is try to figure out a value of A, and then you get a value for root 2A, right? So now you have only one A remaining. You probably need an equation. Using this equation, you'll be able to figure out what's the value for A. Who can tell me what kind of equation can help me to solve the value for A? Now, please post your answers into the group chat, right? And then I'll be able to see every single person's answer to it. Yeah, I see still Gabriel has the correct answer. There's so many ways, right? You can use the Stewart method. This is a triangle. This triangle, you already know every single segment. Using the Stewart, using a big equation, you get what you need. Or you can also do a very quick thing. You don't have to use Stewart. Let's just focus on this little triangle. I'm going to change the color back maybe. Let's just focus on this little triangle. You already know this is 60 degrees, right? Try to use a cosine law. In this cosine law, in this triangle, build up a cosine law, you get what you need, right? So could be Stewart or just a cosine law in triangle BAM. Okay? Because the cosine law is going to generate an equation which only contains A as one variable. That's it. Does it make sense? So we don't have to go to the details, do all the calculations, blah, blah, blah. So you understand where I come from. Right? With all those information, you're going to find a value for A. And then bx squared will be just 2a squared. Plug in the value, you'll be able to see A is the correct answer. That's it. So far, so good? Right? This is something quite understandable. You see, you're not using something so complicated. You just have to follow, as long as you angle bisector, use the angle bisector rule. As long as you see our pattern, the birdie shape, you use the similarity, and then the problem will basically speak for itself. So far, so good? All right. If all good, let's go to another problem. Okay? Let's go to another problem. This time, let's go for an AIME problem. Let's go for AIME problem. This is a problem that comes from, see, 2015. AIME 2, question number, AIME 1, question number 11. Okay, so the problem says triangle ABC has a positive integer side length. Oh my God, as long as you see this, positive integer side length. You see, something does not have to be a positive integer. A side length could be fractional numbers, like whatever, right? Something does not have to be positive integer, but happen to be positive integer. There are only two reasons. These are all the conditional react I want you guys to remember. As long as you see some side lengths that are positive integer, one thing is you're probably going to use some number theory. Maybe some factorization, blah, 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 right? This could be one thing. Or you might use some inequality. So what do I mean by inequality? Let's say at the end of the day, you find a value A. A is between 3 and 3.5 to 4.5. So the only positive integer in between is actually 4. Right? So in the future, as long as you see something does not have to be a positive integer, let's say your age has to be a positive integer, right? So it doesn't matter. But something like the side length, something like the angles measurement, if it does not have to be positive integer, but the question forces it to be a positive integer, most likely you're going to either use number theory factorization or using the inequality to squeeze them out. These are the common practice. I don't know you're going to use which one, but I'll just tell you this is the common practice. Okay? So let's continue, right? So this is how you read a problem. So whenever you read a problem, there's so many things pops up, right? This is like the way how you can be more accurate, you can be faster. If everything you need to think from scratch, you're going to take forever to finish this exam. Okay, so let's continue. Triangle ABC has positive integer side lengths with AB equals to AC. I be the intersection between the angle bisector. You see, they keep using this angle bisector of A, of B, and C. Suppose BI equals to 8. What is the smallest possible value parameter of triangle ABC? Okay, let's go for the shape. This is your shape, goes like this, this. Okay, this is very symmetric shape. You have like A, B, C, I, D, right? Two BI, CI, two angle bisectors, they intersect each other. And you know the BI has a length 8. And these are all angle bisectors, right? So like I said, as long as you angle bisector, try to write down angle bisector law. Angle bisector Then you have AI over ID equals to AB over BD, right? Well, this problem, okay, that's pretty much everything, right? That's pretty much everything the question gave you. And then the question asks you to determine the smallest possible of the parameter of ABC. Well, if you want to determine the parameter, you probably want to say this is maybe A, this is A, this is B, right? This is half of the B because there's not too much, right? You can just basically put it in. Okay, if that's the case, you see, you use the angle bisector, set up the angle bisector theorem. You know, like BI is 8. So maybe you just need to do some calculation, build up some relationship between A and B and 8, right? Hopefully taking from there, you figure out what you need. So let's have a quick look at it. If you want to use 8, 8 is here. If you want to use 8, I think the most straightforward way is try to put it into a triangle using some triangle relationship, right? Because you want to build up a relationship between A and B. What is the most straightforward way? I think, you see, 8 is here. It's just right in the right triangle. This right triangle has one side BD, one is 1 over B. One is like a B over 2, excuse me, right? B over 2. So as long as you can figure out the other one, hopefully using A and B, then it's very easy for you to build up the relationship, right, between A and B, and taking from there, hopefully you get what you need, right? So you see, you already have this angle bisector relationship. AI over ID equals to AB over BD. And also you can find out AD itself actually equals to A squared minus 1 over 2 B squared, right? Using a basic Pythagorean. Then you will be able to determine the measurement of ID, right? You'll be able to determine the measurement of ID because AI over ID equals to this guy, and they're adding them together equals to AD. So you'll be able to determine what's the value for ID. ID is a pretty nasty number. A squared minus B squared over 4, B over 2, A plus B over 2. Right? This is your ID. Because like I said, the question asks you to determine the minimum value of your parameter, 2A plus B, right? So what is the minimum value of this? I think you need to build up the relationship between A and B, right? And hopefully you cancel one parameter and then take it from there, you get what you need. So just in the right triangle, you use the Pythagorean theorem, right? 8 squared equals to ID squared plus 1 over 2 B squared. That's pretty much what you can do, right? So putting them together, there will be some calculation. So this is an AIME problem, right? So you have to definitely do some calculation. The calculation just give you the value for A. A equals to 64B, B squared minus 128. Okay? Now you figure out a relationship between A and B. Okay? So far, so good? It makes sense, right? Now you are trying to find out the minimum value, which is 2A plus B minimum, aka 122, 128, 128B, B squared minus 128 plus B. What is the minimum value? That's exactly where you come from. Okay, now how can I figure out the minimum value of this 128B over B squared minus 128 plus B? Oh my God, this is too complicated. I don't even know how I can continue with that. You know what? Previously, okay, let's go back to our regular thinking routine, right? So like I said, as long as the question gives you the positive integer relationship, so most likely you're going to do two things. One is the number theory related thing. One is the inequality. I think you guys should be more familiar with the number theory related discussion. Let's say, I want to give it an example. Let's say this is a relatively complicated expression, but if I can do some magic, I can times A times B into a number, or maybe A times maybe B squared minus 128, like whatever, equals to a number. I can use the typical number theory way, right? I find all the factors for the number, assign them to A, to B. I do some casework, figure out what is my value A and B. That's it, right? This is one solution. Well, the downside is here, you know, A, B, this is not an easy expression, right? They're like all over the places. If you put them together, you're going to have like what? A over B times B squared 128 equals to 64. There's no guarantee you have A over B as an integer, right? A and B as integer is good, but A over B, no. So that being said, if you go such approach, maybe not so doable, right? So in that case, maybe we have to go for the second approach. Is it possible for me to figure out some inequalities? And taking from the inequality, I'll be able to figure out what's the value for A and B. So this is more like we talk about some intrinsic inequality for a triangle, like we discussed at the very beginning. Let's focus on this. Let's focus on this. For this triangle, so first of all, I can claim this triangle must be an obtuse triangle. This must be an obtuse triangle. Why? Why it cannot be a cute triangle? Why it cannot be a right triangle? This is very understandable. Let's do a quick calculation because let's say this is angle 1, angle 2, angle 3, angle 4, right? 1, 2, 3, 4, they're all the same, right? Because this is like isosceles triangle. I understand angle 1 plus angle 2 is equals to angle 3 plus angle 4. There must be lesser than 90 degrees. Is it right? You cannot have two bottom angles more than 100, like 90 degrees. So the total will be more than 100, like more than 108. So that being said, angle 2 plus, okay, let's see. 1 plus angle 2 equals to 3 plus angle 1 plus angle 2 equals to angle 3 plus angle 4 lesser than 90. So that being said means angle 1 or angle 2 is equal to angle 4 lesser than 45 degrees, right? Angle 2 plus angle 4 lesser than 45 degrees. They're both less than 45. If those two less than 45, adding them together will be lesser than 90 degrees. So this must be angle greater than 90 degrees. Does it make sense? For a isosceles triangle, like the bottom two angles make two angle bisector. So this triangle must be an obtuse triangle. So what I'm trying to say means what? So I'm going to put it here. Now I have a triangle here, BIC, right? This is more than 90 degrees. This is 8. If this is not more than 90 degrees, this is just 90 degrees. I know this is not happening now, but I'm just trying to say, if this is just 90 degrees, 8 will give BC equals to 8 times root 2, right? But for now, the top angle I is greater than 90 degrees. So this guy, BC, will be greater than 8 times root 2, right? These are the intrinsic properties for any triangle, like a bigger angle facing a bigger face, like a bigger side, right? The bigger angle always go for a bigger side. So that being said, it means for now, my BC, which is equal to B, will be greater than 8 root 2. But I need an upper limit, right? I cannot like be whatever big it is, right? I need a range. Who can tell me what is the upper cap for my B side, BC side? Now I have one cap. BC must be greater than 2 root 8, 8 root 2, excuse me. But BC cannot be as big as possible. There must be some other constraint the value of my B. Who can tell me? Yes, I see somebody has answer right away. B must be lesser than the two sides sum, right? Any two sides, putting them together must be greater than the third one. This is the intrinsic property of the trigonometry. Nothing too flowery, nothing too complicated, right? So B must be lesser than 16, greater than 8 root 2. So now 8 root 2 is actually 11.3 something. So do not have too much options for B. B could be what? 12, 13, 14, 15. Is that right? You know what? The remaining part is fairly easy. As long as you know the value of B, put it back, figure out the value of A. A might not be an integer, right? Just try to make sure A is an integer. But even though A is an integer, you can just try them for and then figure out what is the minimum parameter. And then that's it. So the next one is going to be let B into A, find the value of A, and then compare the parameter of the triangle. That's it. You see, this problem is also question number, AIME question number 11. But we're not using something too flowery. Some angle bisector, some intrinsic properties of the triangles. This is exactly where we come from. Okay, so far so good. Are we all on the same page? Okay, any questions, just let me know, okay? So that being said, we actually give you guys 3 problems. They're all question number 25, 24, right? Or some AIME number 11. I just want to show you sometimes you don't have to be scared. Some difficult problem, as long as you scratch the surface, dig into the essence of the problem, you can find out this is actually just use the basic concepts. Sine law, cosine law, angle bisector, Pythagorean, nothing than that. Right? We're not using some complicated, very complicated theorems. Basic concepts is really going to help you to solve all your problems. So far, so good? So this is our category number 1. I think using 3 examples is good enough. It already shows you how to use the basic concepts, try to do all those relatively complicated problems. Now let's fly to our second category. Similarity. Like I said, as long as you see some similarity problems, and the question asks you to do some area, like whatever, try to use the similarities ratio, perfect square equals to the area ratio. This is really going to help you to significantly expedite your calculation process from time to time. Let me give you an example. Number 2. This is our example. Okay, we're looking at a problem that comes from 2023, our last year, AMC12B, question number 25. The last problem for last year, AMC12B. If you check the official solution for this problem, it's super complicated. But let's try to do some easy ways we can solve the problem in about maybe 1 minute maximum. Let's have a quick look at it. A regular pentagon with an area root 5 plus 1. Okay, regular pentagon. You see, regular pentagon, regular hexagon, you see that from time to time. They always keep giving you this kind of less like a vehicle, right? Like a problem vehicle, and then give you all the flowery things to this. A regular pentagon with an area root 5 plus 1 is printed on paper and cut out. The 5 vertices of the pentagon are folded into the center of the pentagon creating a smaller pentagon. So what is the area of the new pentagon? So this guy, I think you need a graph, then you will understand where this is number 2. Oh no, number 2. Okay, I'll show you the graph. This is the graph. So basically, you have A, B, C, D. This is the big pentagon. And then the question says you just basically fold all those 5 different vertices into middle, and then you'll be able to create a new, like a smaller pentagon. So you see the dashed line here is more like a fold, like you're kind of like your folding trace, right? You fold it. Like the way how you fold it, you want to make sure that A is actually jump to here, right? A will be superpositioning with the O here, original center O here. So that being said means what? This is going to be what? AM is going to be equals to OM, right? Everything is symmetric. If I do a connection from here, the upper part and the lower part, these are congruent to each other, right? This part and this part, they are congruent to each other, right? I just want to show you how this folding thing works. Okay, so I'm going to remove that. I don't need all those information. Okay, after you blah, 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 do all those kind of dashing, like this kind of folding, you'll be able to generate a relatively smaller pentagon. This is your smaller pentagon in the middle, right? And this pentagon is definitely the new pentagon, like the newly generated regular pentagon. So of course you can find out this pentagon is actually similar to the big pentagon, right? All the regular pentagons are similar to each other. So you'll be able to find out the smaller pentagon is actually similar to the big pentagon. Okay, if something is similar to each other, then you can find out the smaller pentagon's area over the big pentagon's area. The area ratio will be similarity ratios perfect square, right? Whenever I say the similarity ratio or like the side ratio, it does not really have to be real side. As long as there are corresponding segments, they're good. Let's say the height, the angle bisector, right? All those corresponding segments will be proportional, not necessarily always the side. So that being said, let's have a quick look at it. If I want to focus on these 2 lines, OM and ON, these are actually the 2 height from these 2 regular pentagon, right? OM is the smaller pentagon's height from the center to one of the side, and ON is the bigger pentagon's height from the center to the ON. So my goal is try to figure out OM over ON perfect square. OM over ON perfect square. Let's try to do a further simplification. OM was what? OM is actually half of OA, right? I just mentioned because this is a folding dash. So OA is actually, M is actually meet of OA. And then what about ON? ON is actually OA times the sine theta, right? Sine theta. OA can be canceled. 1/2 sine theta is actually sine 54 degrees. Does it make sense? It's a pentagon. Pentagon, you figure out what is the interior angle, right? It's actually n times n minus 2 times 108 and divided by n, right? So you figure out what is like the interior angle of your, like, what should I say? Like, what is your like interior angle of your pentagon, so on and so forth. You find out this is actually 54. Sine 54, still remember? Sine 54, we talked about it. Sine 54 is here. It's actually an angle you need to remember. It's the same as cosine 36. sine 54 equals to cosine 36, right? So therefore, okay, come to here. Yeah. Sine 54 is actually equals to root 5 plus 1 divided by 4. You see? This question number 25, you just need such a one equation. You figure out the value. Like I said, 1 minute, right? It shouldn't be costing more than 1 minute. If you check the official solution from AOPS, it's going to take forever. Super long explanation here and there. But using my way, similar triangle, what should I say? Similar triangles, area ratio is the similarity ratio is perfect square. Plus, you need to remember some special angle. Special angles trigonometry value, you get what you need. Right? Easy peasy. You know, these kind of problems is actually very alike. So if I give you another problem is exactly the same thing, I'm going to save that to our homework. You guys can, so after this lecture, we're going to give you guys the homework. You can go to the homework and try to do pretty much the same thing using find out similarity and then do the area ratio. Whenever I say similarity, does not always mean similar triangles. Could be similar hexagon, similar square, similar quadrilateral. As long as they're similar, right? We're good. As long as we're similar, we're good. Okay? So this is the second type. I think the second type is very mechanical. So we do not have to give you too much similar examples. It's all doing the same thing. You know, like the find out the similarity, find out the size difference, like the size ratio, make a perfect square, you'll be able to get your what is called, you can get your area ratio. Okay, so far so good? All right, if all good, let's go to our last category. Yeah, because normally speaking, the 2D geometry in our regular lecture, we have 10 lectures, 20 hours covered all the details in and out. But now this is only like a high level boot camp. We just do something fairly fast. The third one is let's try to talk something about the circles. The circles could be tangent, could be some Ptolemy, you know, Ptolemy, yeah. Okay, all those kind of things. Okay. So the first one, let's go for an example. Okay. This is a problem from 2018. AMC12B, question number 25. Okay. Sorry, I only give you like the 24 or 25 difficult problems. But I just want to show you those difficult problems actually always have a very easy solution as long as you understand what you're doing. So this problem says what? You have 3 circles, omega 1, 2, 3. Each of them has a radius 4. Okay? And they are placed in the plane. So each circle is externally tangent to the other 2. Points P1, P2, P3 lies on 3 circles respectively, such that P1 equals to P2 equals to P3. So I mean like P1, P2 equals to P2, P3 equals to P1, P3. So basically this is going to be what? This is going to be a equilateral triangle, right? And the line PI plus 1 is tangent to omega I. So basically, you see P1, P2 is tangent to omega 1. P2, P3, P2, P3, P1, tangent to omega 3. So they're all tangent to 3 different circles. Okay? And the area of triangle P1, P2, P3 can be written in the form of that underscore A plus underscore B. What's the value for ABC? So long story short, you need to determine the area of P1, P2, P3. First thing first, if you want to determine a equilateral triangle's area, you just need a side, right? Root 3 over 4 a squared. That's going to be the area of an equilateral triangle. Is that right? So that being said, our focus for this entire problem just need to find out what is the side. What is the side of my equilateral triangle P1, P2, P3, and then we'll be able to solve the problem. But the nasty part for this problem is the P1, P2, P3, they're all like flying there, right? They has nothing to do with a real, there's not something embedded into the circle or, it's just like three tangents, put them together. It's not so easy for me to kind of like measure the value for P1, P2, P3, right? You know what? No worries. As long as you see a problem, you have no idea where to get started. Doesn't matter. Follow our conditional react. The problem will have some conditions that we need to react conditionally. After you list out all those conditional react, maybe the problem will speak for itself. Maybe. I'm not so sure, but we have to follow our conditional react. So what are the conditional react? We have already said circle tangent to a line. You need to do connection between the circle center to tangent foot. Two circles tangent to each other, you need to connect to two circle centers, right? So these are the basic stuff we talked about from day one. So let's just try to do some basic conditional react. We'll see what's gonna happen. So you said P1, P2 is tangent to omega 1. Let me do a connection. This is 90 degrees, right? What else here? P2, P1, they are tangent to omega 2. Let's do a connection. 90 degrees. And what else? Omega 1, omega 2. There's two circles that are tangent to each other. I'm going to do the same thing, right? Two circles tangent to each other. I still have to do a connection between these two circle centers. I'm not doing anything special, right? So this is exactly follow all the conditional react I know from day one. Okay, now what should I do, right? I only know the radius is 4. This is the only thing I know, 4. The radius is 4. The radius is 4. So these together is actually 8, right? Because two radius, right? Two circle center connection is actually 8. Well, in order to do some calculation, I put P1, P2 in, right? Or P2, P3, like whatever. I need to build out some triangles, right? All my magic happens on the triangles. I cannot just let it fly in there, right? Is it an easy way for me to determine some triangles and hopefully taking from there, solve the problem? Let's say if I want to determine the value for P1, P2, for instance, right? You see P1, P2, P3, P2, P1, P3, they're all the same. Let's just take one as an example. Now P1, P2 is kind of like a squeeze between two red triangles, right? My red two triangles, I have it there. But if I want to really determine something like P1, P2, I'd better put it just like as a whole into a triangle rather than shared between two triangles. I think the most straightforward way is let's try to do a quick extension for these two. Okay? Because by doing that, you actually put your P1, P2 into a right triangle, right? Not make it too complicated. That's the most straightforward way. Okay. If that's the case, let's have a quick look at it. Let's have a very quick look at it first. We know this is like 90 degrees. Who can tell me what is the angle for this guy? Is it like an easy angle? Easy peasy angle, or just like a random angle? I have no idea what it is. Yeah, I see Kevin has the correct answer right away. This is actually 60 degrees. Why this is 60 degrees? I can give you a very easy explanation. Let's focus on these two sides. I'll use the color maybe blue. This guy is perpendicular to the black, right? P1, P2. This guy is perpendicular to P3, P2. P1, P2, and P3, P2, they have a 60 degrees included angle. So both of their heights will also have a 60 degrees included angle. Does it make sense? If two sizes, they're already like my, okay, I'll give you the color here, right? I don't know if you guys follow me. The two black lines, they're 60 degrees apart, right? They're kind of like 60 degrees included angle. And I make two heights for those two sides. So definitely the two heights, they're perpendicular to these two sizes, which are 60 degrees apart. So the two heights will be also 60 degrees apart. I think this makes sense, right? This is not something like a rocket science. You guys follow me? Yes or no? It's good, right? If this is 60 degrees, you actually open the door to success because it means what? Means if this is x, I'm going to use the color, this will be what? 2x. And this will be, oops, I have to, yeah, this will be root 3x. Root 3x. Is that right? X. This is x. This is 2x. This is root 3x. Okay. So that being said, for triangle P1, P2, P3, your dreaming line P1, P2 is actually root 3x. As long as you figure out x, your work is done, right? Okay, for now, the $1 million question for you guys is, how can I get this x? How can I get this x? If you want to get a value, this is the thinking process. If you want to get a value for x, you must put it into a triangle, right? Which makes sense, right? The x part at this moment, there are only two triangles remaining. One is this red triangle. One is this green triangle. The red triangle, I think you cannot use it anymore because a red triangle already helped to contribute the x under root 3x and 2x relationship. So its work is already done. You cannot get too much out of x. You cannot get too much of this red triangle anymore, right? It already contributes the under root 3, the 1, the 2 relationship, right? So this is the thinking process. Why you want to use this red? Why you want to use this green? There's a reasoning for that. Because red triangle already helped to contribute to get your x, like under root x or 2x relationship already. So it's already done. You cannot do too much for this. So therefore, you must focus on the green triangle to finish your work. For a green triangle, let me drag it out. Is there something you can still use? I'm going to give you maybe some denotation. This is B. Maybe this is A. I don't know. Maybe this is C. A, C, B. So for this green triangle, AB equals to 4 plus X. BC is the 8, right? BC is the 8 because this is the connection between two circle centers. It's double of your radius, right? What's the value for AC? What's the value for AC? Two x minus 4, right? This is 2x minus 4. And this is your 60 degrees. You know what to do? Cosine law, right? You see, cosine law is all over the places. There's like, yeah, I see Kevin has the correct, yeah, I see Gabriel has the correct answer as well. Cosine law is like so important. It's all over the places. You know what? Even the Stewart theorem, like our Stewart theorem was actually proved by using cosine law. We just don't give the proof, right? So cosine law is like so important. If I do a comparison, sine law is not that much important, to be honest. Cosine law is much more important than the sine law. Okay, so look, with all of this, you have a cosine law, you have a big equation. Oh, of course, I admit the calculation might not be easy, but you use our calculation, blah blah blah, you get a value x is pretty nasty value. 2 root 21, 3. Okay, use this x, you will be able to get root 3x. And use the root 3x, you will be able to get the value of your entire trigonometries. Like in your entire triangle's area. Area is the D part, 552. You see, the process per se is actually very understandable, right? It's a very understandable process. You just have to use our conditional react. You see tangent to connection between the tangent foot and the circle center, or two circle centers, and then just basically follow some easy things. You'll be able to figure out all those difficult problems. You see, you don't really have to know a lot of complicated theorems, and then you can also solve all those problems fairly quick. Okay, if all good, let's go to the last problem of today's lecture. Okay, let's go to another AIME problem. We want to make sure we have some AIME problems, some difficult AMC problems to give you guys kind of like a blended solution and experience for all the problems. So this is here. Give me one sec. Okay, so this is a problem that comes from 2011, AIME 2, question number 10. So the problem says you have a circle. The circle with center O has a radius 25. Okay, I'm going to write it down. The chord AB of length 30, CD of length 14, they intersect at point P. The distance between the two midpoints of the two chords is 12. The quantity OP squared can be expressed into M over N. Find out the value for M plus N divided by 1000. So aka, you need to determine the value for OP. Okay, so how the graph looks like, you always need to have a nice graph. This is your circle. The circle has two, change color, has two chords. Okay, the mid of two chords goes like this. Okay, so it has A, B, D, C, and E, F, P, O. Okay, you have a circle. The circle has a radius equals to 25. You have two chords. One chord has a length 30. One chord has a length 14. E and F, there are two mid, right? Two mid of these two chords. You do a connection between E and F. The distance between E and F is 12. With all those information, the question asks you, what is the value for OP? What is the value for OP? How can I get a value for OP? Well, if I want to find a value for OP, right, I need to figure out some ways, right? I need to put it either in a triangle or something, right? Taken from there, I got a value for OP. But OP is not, it's actually flying there, right? There's a kind of like no way for me to figure out what's the value for OP. Is there something easier for me to determine OP? I need to put it into a triangle or into some other stuff. to make sure the OP could become easier, right? Well, how can I get my value of OP? Put it into a triangle, it might not be so easy, right? Because you might have some random triangle or something. But let me try to do something like this. You see, I have a chord. You see, A, B, and C, D, there are two chords. If I have a triangle, if I have a circle, I'm going to ask you something. If I have a circle, I know the radius of the circle. I know the length of the chord. In that case, can I easily get the distance from the center to the chord? I think so, right? Because this is going to be your R. This is going to be half of your chord. So using a Pythagorean, you'll be able to get the distance between your circle center to the chord. The circle center to the chord, the distance is actually the connection between the midpoint and the circle center, right? So I'm going to do something like this. Here, here. So I can easily get the value for OE and OF. OE is 20, OF is 24. Which makes sense. A longer chord has a shorter distance, right? A shorter chord is far away from the circle center, has a longer distance. So this is going to be our 20. This is going to be our 24. Now, I think many students will think of this. Ah, this is easy. I already know everything about that. So I would be able to find my value of my OP within this little green quadrilateral. This green quadrilateral, for sure, this is what? A cyclic quadrilateral, because you have two 90 degrees there, right? This is 90 degrees, this is 90 degrees. So my EFOP, I kind of having a cyclic quadrilateral. If in a cyclic quadrilateral, I want to determine OP, I can use what? Ptolemy, right? These are a very, what should I say, intuitive process, right? It's OP times EF equals to PF. So using Ptolemy, OP times EF equals to EP times OP plus PF times OE. Let's have a look at it. OP is exactly what I'm looking for. EF is 12. EP, I have no idea EP what it is, right? OP is exactly what I'm looking for. PF, I have no idea what I'm looking. OE is actually 20. OF, I'm sorry. Oh yeah, this is OF, sorry. OF is 24, right? OPEF, EPOF, PFOE. Okay. So that being said, if I want to figure out a value for OP, I need to figure out a value for EP, I need to figure out a value for PF. And then taking from there, I'll be able to figure out a problem. But to figure out the value for OP and EF might not be that much straightforward, right? You know P is their intersection point, but you have to figure out what's the value for this guy and what's the value for this guy. So it might not be so easy for you to figure them out. Yeah, of course it is doable, but you have to do a lot of calculation to make it work. So here, I like to give you a very straightforward solution, a very quick solution, help you to expedite the process. Is that like the complicated one, you guys can check OPS. It has all those detailed things. How to determine OP? OP for this equilateral, EOFP, it is only a diagonal, right? It's nothing really special, but it has some special meaning for this triangle? For this triangle, EOF, what is my OP? Who can tell me? For my triangle, EOF, is there anything special for this OP? This is something you need to jump one step to get an answer. Yeah, I see Gabriel has the correct answer. OP is actually the twice of the radius of the circumcircle. Is it right? It's actually diameter of the circumcircle. Did you still remember we actually introduced a very important property for the area method? If I have a triangle, this is R. The area of my triangle is actually what? ABC over 4R. Is it right? The three sizes, this is what I just mentioned. You see in our, it's actually here. See? ABC over 4R, right? So that being said means what? It means if I want to determine the value of my OP, which is 2R, I just need to get a triangle's area and the three sizes. I'm good. This triangle, you already know the three sizes. Using your Heron's formula, you can determine what is the... Using the Heron's formula, we'll be able to determine the area, right? And then ABC is already there. You will be able to determine the value for R. So Kevin got a question. How do we know this is 2x circumcircle? This is easy because look, these are cyclic. So it means that I must have a circle for that, right? And this is 90 degree. 90 degree must facing the diameter, right? So must be a diameter. This is basically where we come from. All right, you guys follow me? That's pretty much the solution for such a problem. As long as you know this, you know the value. Very easy. Okay, you guys follow me? Yes or no? Right? Okay, that's pretty much what I want to say for our today's lecture. That's our lecture number 1. We talk about the 2D geometry, triangles, and circles, blah, blah, blah. We give you guys some like 3 major categories, how those problems are divided, and then give you a little bit like examples, how to use those examples, those technologies. There's so many things you need to remember, some theorems, conditional React, especially conditional React. You have to practice, make it as an intuition, and then you'll be able to use it for the following lectures. So yeah, no worries. This is only our lecture number 1. And yes, we have some free lectures upon request. You can scan this barcode, take a screenshot for this barcode, and your parents can, this is like WeChat, your barcode. They can ask for some free lectures. But generally speaking, our lectures is focused on the strategies, how to get all the strategies, how to, how to get it. And yeah, for our register, this is only our first lecture is free. And from the second lecture, we're gonna, our registered students, you'll be able to, I think I've already shared you guys all those like the Zoom barcode. So we're gonna go to the Zoom. It's only the first lecture, we're gonna do the live. And yes, from the second one, we're gonna jump to Zoom. And I will release the, what is called, the homework to our Google Classroom. You have 1 week to, check. And everything, all our homework will be quite in line with our lecture. All the technology, everything we introduce here will be 100% applicable for our assignment. So yeah, I think that's pretty much. Have any questions for me? Everything's good? All right. So in that case, I wish you guys a good day, and I'll see you guys for the next week. Okay. Bye, guys.
All right, bye. Thank you.
Bye. Thank you. Bye.